let's look at an example of a mass spring system that has some external forcing just to see what happens when we find a full-blown solution to this sort of thing. So here we have a mass spring system with a 1 kilogram mass, so mass is going to be 1, a spring with spring constant 5 newtons per meter, so 5, and an inertial damper with damping coefficient 4, so 4 newtons per meter per second. And we also are going to have an external force that's given by this function sine of 2t plus 3 times cosine 2t. Okay, so in this case, our forcing function is just a sinusoidal function. I guess this should be in newtons, right? And a force should come in newtons. So with all of this information, we can just write down the differential equation. So it's mass, which is 1, times y double prime, plus damping coefficient, which is 4, times y prime, plus spring constant, which is 5, times y, equals your forcing function. So sine of 2t plus 3 cosine 2t. All right, so to solve this, we need to find the complementary solution. So we can write down the characteristic equation for the associated homogeneous equation. So that's going to be r squared plus 4r plus 5 equals 0. It doesn't look like this factors nicely, so we're going to have to use the quadratic formula, or complete the square, I guess. So r is minus 4 plus or minus the square root of 16 minus 4 times 1 times 5 is 20 over 2. So this is going to be, let's see, minus 2 plus or minus. So this is square root of negative 4 is 2i over 2 is just I. Okay, so our particular solution, remember complementary solution. Remember another name for the complementary solution is the transient. So our transient is going to be e to the minus 2t times some constant, c1, times sine of t, plus some other constant, c2, times cosine of t. And remember, it's initial conditions that determine the constants c1 and c2. We don't have initial conditions, so we'll just leave these as unknown constants for right now. Okay, so we have our complementary solution, our transient, and notice that our transient, first of all, it is transient because there's this exponential decay, which we knew had to happen because the damping is non-zero. Also notice that the complementary solution does not overlap with our forcing function, so we can use undetermined coefficients and we don't need to multiply by a factor of t when we make our undetermined coefficients guess. Okay, so let's fit undetermined coefficients in here. We'll probably need to scroll down some. So for undetermined coefficients with this function on the right-hand side of our equation, our guess for undetermined coefficients is going to be something times sine of 2t plus something else times cosine of 2t. And now we can start taking derivatives. First derivative is 2a cosine 2t minus 2, for some reason I called this c, let's call that b instead, 2b times sine of 2t, y double prime sub p is minus 4a sine of 2t minus 4b cosine 2t. Okay, now we can plug all of this stuff into our differential equation. So let's gather up all of the stuff that has sine 2t in it. And let's gather up all the stuff that has cosine 2t in it, because we're going to set this all equal to the inhomogeneous term, which is sine 2t plus 3 cosine 2t. Okay, so from y double prime right here, this contributes a, for sine, it contributes a minus 4a, and for cosine, it contributes a minus 4b. For y prime, we have to multiply by 4, so when we multiply y sub p prime by 4, for cosine, it contributes an 8a, and for sine, it contributes a minus 8b. And then for y, we have to multiply it by 5, so for sine, that contributes a 5a, and for cosine, it contributes a 5b. Okay, now we can compare coefficients. The coefficient on sine on the left has to be equal to the coefficient on sine on the right, which is 1. The coefficient on cosine on the left has to be equal to the coefficient on cosine on the right, which is 3. So that gives us two equations. So for the red, we get, let's see, it looks like minus 4a plus 5a is a, minus 8b equals 1. And for the cosine equation, we get, let's see, 8a plus b equals 3. So to solve this equation, let's see, why don't we multiply the first one by 8, I guess? So that's going to give us 8a minus 64b equals 8. And then do first equation minus second equation. The a's cancel. We're going to get minus 65b equals 8 minus 3, 5. And so we get b is negative 1 over 13. Okay, and now we can use this first equation. Let's use this first equation to find a. So a plus 8 over 13 equals 1. And so a is 5 over 13. Okay, so now we know a and b. We know our particular solution. So our full solution is the particular solution, which is 5 over 13 times sine of 2t minus b, which is 1 over 13 cosine of 2t. So that's all our particular solution, plus our complementary solution, which was e to the, I don't quite remember, minus 2t times constant times sine 2t plus constant times cosine 2t. Okay, and so there's the complementary solution. And notice that as usual, or as we expected for this kind of system, when you have non-zero damping, the transient here, the transient goes to 0 as t goes to infinity, right? That's what we expected, and this is because this exponential term is decaying to 0, and this sinusoidal term has a maximum amplitude, and so the exponential is going to drag this whole thing towards 0. And the particular solution, the steady state, it doesn't go to 0 as t goes to infinity. So whatever initial conditions you set up, it will deviate from this steady state initially just because the complementary solution will be around. But if you wait long enough, this exponential decay will kill off the complementary solution and you'll just be left with the steady state.